So how is the summer? Like, what is the temperature today? Is 37. Okay. Yeah. So in astronomy, I'll just start sharing my screen. Uh, None? Yeah. Okay. So in astronomy, so this is in centigrade, like 37 or 40, whatever centigrade. Okay. Yeah. So in 40 degrees centigrade, so it's pretty hot. Like, so in physics or in astronomy, we use a different type of thing. Like we use a Kelvin scale. Do you know anyone about a Kelvin scale? How to estimate? Like you just add 273 these values to a centigrade and you get a Kelvin. So Mumbai temperature is kind of like 320 or this in Kelvin scale. But what is interesting, in 5 to 10 minutes, I will talk you about some places where compared to those places, Mumbai will feel like it's a Siberia, like it's very cold. Like Mumbai will be very cold. So to go on those areas, just first I want to mention that human civilization is for here for 5,000 years almost. Like in that time scale, every day we are seeing the sun. So have we noticed ever the sun is changing, like the brightness is decreased, or if someday suddenly the sun is not there, these kind of things doesn't happen, right? So good for us. That doesn't happen. But we'll ask these questions that can it be possible someday these kind of things happening, sun will change its brightness or this kind of, and if this happens, what will happen to us and when it will happen? So these are important questions that we ask in astronomy. And I will try to answer these type of questions. But again, if we just make this place a little bit broader, like not only sun, just talk about other stars. Can we see other? We see there are multiple stars in our sky, and we will ask these questions to those stars also, like how long they are going to live, when they will change their brightness or light, will they change at all? So to do this, we need to see stars. So this is Mumbai sky. So nothing is there, no star is there. We have already completely polluted. This is pollution and we can't see anything, like there is no star. So from Mumbai, we can't do astronomy. We can do only astronomy using a computer in Mumbai. And this is a place in Ladakh. And you can see this wonderful thing. Every dot is a star, almost a star. This is a real picture taken by Dorje. He's a scientific officer in IIA, and this place is Hanley. There are two telescopes. One is Himalayan Chandra telescope, and this is a beautiful place. Like the sky is extremely clear, and all these dots are mostly like stars. Now you can see from this image, there are different brightness. So if I just use this pointer, this dot is very bright. This is bright. These are bright, but there are some dots which are not bright. So this happens for a couple of reasons. Like maybe this star is actually bright. That's why this is appearing so much luminous in the sky. But there might be another case. Like if there is a very big star present at a very far distance, like if a car is coming with a big car is coming with big headlights, but it's coming from far away, we'll see that the lights are smaller. But if there is a car with a very near to us, but with not that much powerful lights, we might even see that car's light is much more luminous than this actually big car's light. So these two things happens because of these things. The car is at a very far distance, the big car. So these also happens for stars. If a very big star is very far away from us, its light will not be even reach to us. But if there is a smaller star like this one, if it is very near to us, then we can see it much more brightly. So this is called apparent brightness in astronomy. So for this talk, we'll not discuss this thing because this apparent brightness, we almost know the distance for each of these for different stars. So we'll just talk about their intrinsic light, like what they are producing. So you have all heard that stars or suns, they are burning some fuel, some kind of fuel inside them, and this is creating the light. We will only talk about those intrinsic light. We will not talk about this apparent light for which is coming to the different distances because stars are present in different distance. So yes. It's visible?
Yeah. You can hide it.
Yeah. Yeah. So just first talk about, so what is Earth's size? So Earth's diameter is like 6,500 kilometers, 400 kilometers. So from my home to Calcutta to Mumbai is kind of 2,000 kilometers. So it's big. It's big. It's compared to us, like it's a huge distance. It will take some time to go. But sun is 700,000 kilometers. So you can fit almost 100 Earth inside sun. So sun's size is big, huge. But what about the distance between Earth and sun? It's 150 million kilometers. What does mean that you can fit 200 sun inside this distance. So now it's even more, like it's huge distance, but this is not the end. So we use another distance so this is called 1 AU, this distance between Earth and sun, because this is, we are very familiar, this solar neighborhood is thing. So we give it a name, that 1 astronomical unit. So it's almost 200 Earth radius. So 200 sun's radius. So sun's radius is denoted by this R, and there's a small dot. This is the symbol of sun we use in astronomy. But you have probably heard in science fictions that there is a light year. So in 1 year time scale, light travels. Yes, please come. How much distance light travels? So it's almost 10 to the power 13 kilometers. So that means from a light to travel from sun's surface to the Earth's surface, it will at least take 8 minutes to come. Okay. Then there is another even more distance that is actually used scientifically. This is called 1 parsec. And this is almost 3 light years, more than like 3 into 10 to the power 13. So this is bigger than 1 light year. And then we use also kiloparsec. This is thousands of parsec. You can even imagine these distances. Then there is megaparsec. So each of these different field of astronomy, we use different type of distances. So if we are going to study Earth-like objects, planets, all these things, then we mainly focus on AU, this kind of distance, solar radius. And if we try to study our galaxies or stars which are far away from us, we will use parsec. Then there is another field called cosmology. If we want to study cosmology, then we use megaparsec, 10 to the power 6 parsec. It's a huge distance. Again, taken by Dorje. This is a beautiful picture. Do you know what are these dusty region and what are these bright region is? This is actually our galaxy. So we belongs to this galaxy. So we are part of the solar neighborhood. Sun is our star, and we are there. But we also are a bigger part of these things. We are also part of a bigger thing which is called galaxy. The name of our galaxy is Milky Way because it looks like a milky region. So we are inside a galaxy, so we can't take a picture of the galaxy. We haven't been able to go outside of the galaxy because our spaceships are not that advanced. But we have different measurements, we have different theories, and from these we have made an artistic image of our galaxy, which is pretty much scientific actually. So this middle region, this is very luminous region, and these are the region where stars are being born. And you can see this is a face-on image of our galaxy, of our Milky Way galaxy. And you can see there are different arms. This is a spiral galaxy. There are different types of galaxy we have seen using our telescope. So some of them are elliptical in size, but our galaxy is a spiral galaxy that we have observed. So in this first figure, this is actually a spiral arm. So I'll show you that. So this is where we belong. Like this is the region where the sun, earth systems are there. So this is almost, as I was telling you, that parsec is our unit of distance. So it is almost 8,000 parsecs away from the central region. We are nothing special. We are just a part of this small region. So there are billions of stars present in our galaxy. And so what is the diameter of this thing, of our galaxy? It's 25 kiloparsec. So even if we make a spaceship which will take, we are not that advanced to make this kind of spaceship, but even if we make a spaceship which travels at the speed of light, it will take thousands of years to go from here to here. But we can do observations in different region of this galaxy. And the width is 3,000%. So the galaxy is kind of a disk kind of structure. Its its diameter is very high, but in compared to its diameter, the width is not that much high. Like it's 25,000 kiloparsec, it is only 3 kiloparsec. And inside our galaxy, there are billions of stars present. So do we have actually counted the number of the stars? Actually not. We didn't count all these billions of stars. Actually, we have an estimate of our galaxy masses. And from their masses, we know that each individual, like humans, like each individual will mass around something, some values like 50 kg, 60 kg, 70 kg. So stars are also have some masses. So from that, we have an average estimate. There are billions of stars present in our galaxy. So we'll focus on the birth of these stars, and in this talk, and then we'll talk about how these stars evolve, like a human being, how humans are born, then they evolve, then they at the end they died, and also these things happens for stars also. They will also die. And within 20 minutes, I will tell you that we are actually connected to these stars. We are actually stardust. Humans, everything in this world, we are actually connected to these stars in some way. I will tell you about how we are connected. So again, I love this picture, so we'll coming back to this picture again and again. So there are different brightness of stars present in the picture. So you can see this is very bright, this is not that bright, these are bright. But there's another thing present in the picture. Can you tell me? So there is a difference between this block and there's a difference between this thing. There is a difference. Can you see the difference? Like what are the difference? This thing and this, any color wise? Yeah, the color is different. So what is the color of this star? Is yellowish orange. And what is the color of this star? These or these stars? It's bluish. So from this information, we can tell a lot about these stars. Just hold on. So just to give you another, just to tell you about another thing, that this image and this image, there is a similarity. I will show you. That this star, just focus this star. This is the same star. So this is called the Orion constellation. I will again and again show you this kind of picture. So this is called Orion constellation in English, and these are the different stars. This star is called Betelgeuse. This is called is Rigel, and there is Bellatrix, and these are the 3 stars. So you have Heart of the Hunter, the big hunter. This is actually the constellation. This constellation. We will be revisiting this thing again and again. So this is called Orion Nebula. Again, we will focus on these 2 stars. As you pointed out, that this one is yellowish orange, and this is kind of a bluish. So you have heard about a black body. So black body is nothing but it's kind of a lamp or an oven. Like if you see a oven is very hot, like red hot, you will see that the temperature is too high, and at that moment the color is also very red. So if you have seen those old electric heaters, you will see the coils, they get very, very red, and the temperature is also then high. So from that color, actually you can tell what are the temperature on those coils. This is the property of black body, that from colors we can actually tell the temperature. And this is also true. The stars, planets are good approximations of black body. They are not exactly black bodies, but they are good approximation of black bodies. So this is a detail. This is a much more cleaner image of Betelgeuse, which I was showing you here. So this is Betelgeuse. This is the Orion constellation, and this is the Betelgeuse. So now you can clearly see this is kind of yellowish orange. So from black body spectrum, if we just put all the temperature numbers, so you can see that 1000 Kelvin, if the temperature is 1000 Kelvin, so it's pretty hot compared to us, then the color of the object will be something reddish. And if it is 32,000 Kelvin, then it will be bluish. So Betelgeuse, that is yellowish kind of thing. So what will be the temperature of Betelgeuse? Around 4000 Kelvin. It is actually estimated the temperature is 3600 Kelvin. So just looking at the color of these stars, we can actually tell the surface temperature of these stars. So this is probably this is around 200, 400 parsecs away these stars are. But without going there, just seeing the color of these stars, we can tell the temperature of the surface. And for Regal, it is bluish, you can see. So bluish something, it will be around some 15,000 and 16,000. So this is actually 13,000 Kelvin. So then we see them as a disk in the sky, like. So this is kind of a disk kind of structure in the sky, and they are emitting lights to us. Yeah. Yeah, so exactly. Thanks for the question. So the question is for online audience. When we tell a temperature of a star, what temperature we are actually quoting? So we are actually telling the surface temperature of the star. So, it's the outer envelope, outer boundary. Because I will tell you that we can't even go inside the stars. It's extremely dense, extremely hot, so you can't just go. But we can take information from the core of these stars. There are ways to take that. Yeah. Uh, but yeah, in human case, we can go up to this yellowish, this kind of temperature we see around. So that's why we think they are too hot. But actually, blue, this kind of region, they are much more hotter. So yeah, if you get the full spectrum, then these are hotter. So you can't into everyday's life, we don't see this 4,000 Kelvin, 8,000 Kelvin temperature. So I was telling you these stars are like approximately black bodies. So this is actually a proper spectrum of a star. So these are called wavelengths. You don't need to put more attention in the numbers. So this is the energy. So you can see there is a peak in the distribution. So this peak corresponds to some wavelength, and this gives a temperature. Like this is a star with 6,000 Kelvin. But the things to notice, there are some kind of stripes present in the star. So this is happening due to the absorption or emission of different materials. So what is happening? The sun's light is coming, but in the outer envelope, there are multiple type of elements there. So they are cold. The sun's core or these regions are hotter, but the outer envelope is a little bit colder. So they will just absorb some light and they just dip the light. So it is, if you think of as a light intensity, just intensity drops. It's just don't need to pay attention, just to show you that how actually stars spectra looking. But yeah, as I was telling that you can see these things as this kind of structure. So there is an area of this thing. So area is just estimated. If we think it as a circle, we can estimate its area like pi r square. So it will be the area of that thing. So now we are trying to estimate. What we are trying to estimate is we have estimated the light. We have seen the color. Now we are trying to estimate how much light is coming. That's what I was talking about previously. That how much light the star is actually producing without taking care of distance. Like distance, we know the distance. So these are in kind of a disk structure. So we'll use the area of this disk. So area, and there is a law called Stephan's law that governs the temperature of black body. So you just don't need to know about this. So you just follow the r square and t to the power 4. So this is the radius of the star, and this is the temperature, surface temperature of the star, as she pointed out. So now just think that if the temperature increase by factor of 2, so it will actually goes up 2 to the power 4, means 60. A huge increase. So if there is a small change in temperature, the emission of light is huge. Even it is true for radius. If there is a small change in radius from one star to another star, the emission of light is huge. So that's the reason. So to put all the stars in one diagram, we use a log. So log, what is the log plot does is log is compress everything. Like you can put big numbers in one plot. So we'll use a log plot of this emission of this light which are emitting from the stars. And this is the kind of plot which are very famous in astronomy. This is called HR diagram. We always use this plot. So I just go through this plot. So first, this is called x-axis, this horizontal line. So you don't need to understand all these details, but you just think it as a from here to here, the temperature is increasing. So if some star is present here, the temperature is low. If some star is present here, the temperature is high. Okay. So in this line, the temperature is increasing from right to left. And this horizontal line, from down to top, the luminosity, the light emission from the stars is increasing. And you can see that here is 1, then 100, then I think it's 10 to the power 4. And so these are present in log scale. So that's why the increase in light due to change in radius and temperature of a star, it's huge. That's why to put all the different stars in one figure, we use a log scale. So yes, so we'll start from the small sphere. So these are the representation of different types of stars. So first, the interesting thing is this. Yes. Huh? Uh-huh. Yes, this is the relation. Like if the temperature rises a little bit, like 100, it will, the luminosity will rise 10 to the power 4. It's a log scale. It's a polynomial order relation. Like it's too fast. Like if there is, the more the power is, the 4, it increase faster, very fast. So yeah, that's the relation. Like if it is 2, the exponent, then the increase in temperature will be little bit less compared to 4. If there is a 4 in the temperature, then it will dominate. So because there is a higher power, but that also depends on the different values. What are the values are changing? I'll show you that each and every. So we'll start from here. So these are the stars again. These are the red stars. So what will be their temperature? If it is a red thing, so in astronomy it will be less temperature. So it's less than like 2500 Kelvin. But compared to less, not like our, it's very high compared to us. But in the world of stars, they are less temperature. They have less temperature. And for this reason, so what will be their luminosities? If we follow this formula, the temperature is small, the radius is also small for these stars, and you will get a low luminosity. Okay. So now if we go up to this line, so that means we are going in this direction. So there is something we are increasing. So that means the temperature around these things, if we go this direction, temperature increases. Okay. So from these red small stars, if we reach sun is yellowish, as you can see. So it's have a moderately high temperature compared to these stars. It's kind of a 5000 Kelvin. So sun surface temperature is actually 5000 Kelvin. And because of the increase in temperature, the luminosity increases. And then if we go Sirius, the brightest star in the sky, you will see it's almost becoming a blue star. So that means the temperature is very high and the luminosity is also very high. But you can see that if you go in this direction, the temperature is high, luminosity is high. But suddenly there is a branch from this part. So this branch is very interesting. So these are called giants. So giants means now this R is very high. Okay. So even if now you can see these are some red orange stars. So the temperature is low now. So temperature is almost like a 3000, 4000 Kelvin. But you can see the luminosity is very high. So this color of this blob and this blob are same almost. But the luminosity is very high. And this is happening because their radius is very big. So that's why they are called giant stars. Sun is not a giant star. And we are very thankful to this because Sun is not a giant star. So then there is Aldebaran. It's called Rohini also in Hindi. So I'll show you that how big Aldebaran is actually. And then you can see the Betelgeuse, which we are talking about previously. Now Betelgeuse, these are the super giants. These are the even bigger than the giants. So their luminosity is much higher. Although their temperature is almost similar, kind of 2500 Kelvin, 3000 Kelvin. So they are not hot, but they are very giant, very big. So that's why the luminosity is too high. Like the amount of region they are covering and the light is coming out from the region is too big. So that's why we are seeing much more light from this star. So, huh? No, actually, that's the point. Like, yeah, so the question is these stars might be too far also, but we have estimated their distance. We know actually their distance. So that's why we are comparing. So in this plot, whenever I am saying about luminosity, we have taken care of distance. So they are in the same, we are always taking their internal light. We are not taking care of this thing like if they are far away, what will be the light? Ha, ha, ha. Luminous. No, no, not R is radius. Yeah, radius of the star. So it's the intrinsic light. We are taking care of distance. We know the distance. So we just converted our apparent. We just put it side of the yes. Huh?
Just assuming all these points.
Not
Like,
not the equidistance. We have taken care of each of their distances. Yes, very high temperature. Not really. Yeah, that's the catch point. Like if we include distance and if the like sun is the brightest, okay, in ours, if we see sun is the brightest, we can't see anything. But sun is not the most luminous. Whenever the sun is not there, you can see the Sirius is the bright because Sirius is far away from us. So that's the point. Like sun is nearer to us, so that's why we are assuming that the sun is the brightest because they Sirius is far away from us, Betelgeuse is far away from us. That's why their brightness is low. But here we have taken care of that thing. So that's why here we have corrected that okay, sun has to be there will be much more. Yes, I will come back. Okay, so this is that what we are discussing. So there is we are taking an so we are taking an assumption that is called a black body. So stars, planets, these are approximately black bodies. So what is that? If you see a oven, if it is red hot, then you can tell its temperature is too hot. And if you, from the same point of view that if you see a star is bluish and oranges, you can tell the temperature of that star. Just approximating as a black body. Yes, I'll come back. Huh? Yes, using the color. Yeah. Yes. That's a very good thing. Yeah, the Red Sea. But in we are talking all of these things. Uh, so all of these stars are inside our galaxy. So Red Sea matters when you are going to. So these are all kiloparsec distance. It doesn't matter Red Sea, but these are all nearby stars. So Red Sea will not matter that much. But if you are doing cosmology, which is a yes, you have. Oh, you have. Huh. Uh-huh.
that same sun that we need some other gas.
Hey,
We each still say yellow or the color.
the color will so that color first of all if sun is in some other galaxy will probably not even able to see but the color will be same like the temperature it's related to the intrinsic properties So the color of the sun will be same, but the light will not provide.
Morning, afternoon, the color varies.
Might be color, color might differ, but what we are talking about is the intrinsic color. So this red shift,
The point is the different.
Hmm.
But
We-
the distance will-
huh. So redshift is happens due to a distance change. Okay, so what is mentioned, but we know the distance. We are claiming that we know the distance, so we'll correct it for redshift. Light will change, but I am talking about everything for intrinsically, like which its own property. So that's why I am telling that if we connect, it will sun is yes. Uh-huh. Yes. So sun comparative to Betelgeuse is a giant star. It's pretty old, but there is another thing that giants move too fast. I'll come to all of these things. So Betelgeuse is a very interesting position. If you have heard, if you've heard news, so Betelgeuse is almost going to we believe that it will become a supernova, which is called a supernova. So it will just blast. So it is, you can say it is or at the end part of his life. It's a giant. So it's